Now student, we are going to solve question number 8.14, and in this question it is given to you a Saturn year is 29.5 times the Earth year. Clear? So in this question we can write like this: time period of this Saturn, this is equal to 29.5 times of time period of Earth. Clear? Now how far is Saturn from the Sun if Earth is 1.5 into 10 to the power 8 kilometer away from Sun? Clear? So it is also given the distance between Earth and Sun. We have 1.5 into 10 to the power 11 meter. Clear? Now what is my objective? My objective here is to calculate distance between Saturn and Sun. Clear? So let's suppose I am writing this is equal to RS. Clear? So from here we can say, actually we can write here one expression, that is T square is directly proportional to R cube. Clear? It is given to you T square directly proportional to R cube. So we can write like this: time period. We can say time period of a Saturn divided by time period of a Earth, this whole square, this is equal to distance between Saturn and Sun. Clear? Saturn and Sun, and we can say distance between Earth and Sun, and this is whole cube. Clear? Now we can put here all values. Clear? So now our objective here in this question is to calculate value of RS. Clear? And we can say RE. RE is given 1.5 into 10 to the power 11. Clear? And this is equal to whole cube. Clear? Now it is equal to, I can say TS upon T. Clear? So TS, directly we can say this is 29.5 TE divided by, I can say this is TE and this one is whole square. Clear? We can say this T and T, this is cancelled out. Clear? So from here we can say RS divided by 1.5 into 10 to the power 11, this is equal to 29.5 and power we can say 2 by 3. Clear? So now we can say, let's suppose approximately we can take this is 27 for example. So we are taking if 27, then we can say this 3 cube. Clear? So at the time you can write like this: RS, this is equal to 1.5 into 10 to the power 11 multiply. Clear? Multiply 29.5 we have. So we can say here we are getting only 3 and that is square. So I can say it is multiplied with 9. Clear? Yes or no? Because this is 3 cube, cube and cube is cancelled out. Clear? And we can say 3 square, that is equal to 9. Clear? So from here you can say we are getting that is 13.5 into 10 to the power 11 meter. Clear? So definitely you will get here values more than 13.5. Clear? So approximately if we take into consideration of a term 29.5, we are saying, let's suppose this is 14.5 into 10 to the power 11 meter, or we can say this is 14.5 into 10 to the power 8 kilometer. Clear? So we can say this is distance between Saturn and Sun. Clear? So this is all about this question. Now we are going to discuss question number 8.15, and in this question it is given to you a body weight 63 Newton on the surface of Earth. Clear? So let's suppose I am taking here first situation. This situation is given to you. Let's suppose here we have, let's suppose this is Earth. Clear? And let's suppose I am placing any object on the surface of Earth. Clear? And it is given here, it is having weight 63 Newton. So I can say here MGE, this is equal to 63. Clear? It is given to you. What is gravitational force on it due to Earth at a height equal to half of the radius of Earth? Clear? It means now situation changes. Let's suppose now this is Earth. Clear? And just a minute. Now let's suppose if I am taking this is the Earth. Let's suppose we can say this is Earth. Clear? This one is Earth. Clear? Now let's suppose we are bringing this body to a certain height. Clear? And value of h, this is given to you half of radius of Earth. So I am saying this is let's suppose RE divided by 2, and this value is given to you. Clear to you? Now my objective here, what is weight of this body at a certain height? Clear? So actually you know variation of g due to height, this is given by one formula, gh equal to g divided by 1 plus h upon RE whole square. Clear? So from here we can write like this: gh, this is given by g, we can say directly you can also write like this. Now first important part you should understand, you cannot write here formula GH equal to G1 minus 2H upon RE. Why? Because here this height is comparable with radius of earth. Clear? So now we can write like this, GH equal to G divided by 1 plus, now value of H is given to you RE by 2. So I can say this is RE by 2 multiply RE, and we can say this is square. Clear? From here I can say RE and RE, this one is cancel out. So we can say value of G divided by 1 plus, I can say this is 1 by 2 and this one is whole square. Clear? So from here we can say this becomes 3 by 2 whole square. Clear? So GH, this GH, it is given by G and this is 3 by 2. So we can say that is 4 by 9. Clear? So now we can say what is weight at a certain height. So I can write like this, weight at a certain height, it is given by mgh, and this is equal to m multiply g, and we can see this is 4 by 9. Now it is given in a question mg equal to 63 Newton. So we can write like this, 4 by 9 multiply 63. So we can say this is 7, and I can say here we are getting weight, that is 28 Newton. Clear? So weight of a body at a certain height, that is equal to half of radius, and this is equal to 28 Newton. Clear? So this is all about this question. Now we are going to discuss question number 8.16, and in this question it is given to you, assuming the earth to be a sphere of uniform mass density. Clear? So let's suppose I am drawing here earth. So let's suppose this is a diagram of earth. Clear? For example, this is earth, and let's suppose we are assuming this earth as a sphere having uniform mass. So uniform mass, fine. How much would a body weight halfway down to the center of earth? So let's suppose I am assuming this is a center O. Clear? And let's suppose initially we have a body at a surface of a earth, and after some time let's suppose we are bringing this body to a certain depth. Clear? And let's suppose I am saying this value is d. According to this question, it is given to you that this body is going halfway down to the center of earth. It means I can say this is equal to RE by 2. Clear? Now do you know, if we are taking here this depth from surface of earth, what is value of g? What is variation of g? So variation of acceleration due to gravity due to depth, this is given by one formula, GD. GD is given by G, we can say 1 minus d upon RE. Clear? Where d is what? D is a distance from surface of earth. Clear? So now we can write like this, this is equal to G 1 minus d. D is given to you RE by 2. RE divided by 2 multiply RE. Clear? So I can say this RE and RE, this is cancelled out. So from here we can say this is G 1 minus 1 by 2. Clear? So from here we can write like this, this is G divided by 2. Clear? So I can say GD, this is equal to G by 2. Clear? So now we can say what is weight. So if we multiply m with both sides, so I can say this is mgd and this is equal to mg by 2. Clear? So now we can say what is weight of a body at this position. Clear? So weight of this body at this position, this is given by 1 by 2 times of weight of a body at a surface of earth. Clear? So at a surface of earth, it is given to you, this body is having 250 Newton. Clear? So from here we can write like this, 1 by 2 multiply 250, and this should be equal to 125 Newton. Clear to you? So we can say here this is a weight at a certain depth. Clear? So correct answer we have 125 Newton. Clear? Now dear student, we are going to discuss question number 8.17, and in this question it is given to you, a rocket is fired vertically with a speed of 5 km per second from earth surface. Clear? So let's suppose here I am drawing one diagram. So concentrate, and let's suppose I am saying this is earth. Let's suppose this is earth. Clear? And we are firing a rocket from surface of a earth. So let's suppose here we have a rocket. Let's suppose this is initial position of rocket. Clear? It is given here we are firing vertically with speed 5 kilometer per second. Okay, fine, clear. Now our objective in this question is here, how far from the earth does the rocket go before returning to earth, clear. So let's suppose this rocket is going at a certain height, and let's suppose at position B its final velocity becomes 0, clear. Now let us try to understand why this velocity of this rocket is decreasing, because this rocket is going under the influence of gravity, clear. Under the influence of gravity means we can say the force of gravitational force that is acting in a downward direction, and the direction of motion of this rocket in upward direction, clear. So definitely we can say that force is actually behaving just like a retarding force, clear, and we can say its velocity decreases with height, clear. So let's suppose I am assuming here total height or total distance between A and B we have, that is small h, clear. Between A and B we have distance that is small h, clear. So now our objective is what? Our objective here is to calculate value of h, clear, value of h. So now you can see this rocket is going under the influence of gravity. It means we know that gravitational force is a conservative force. Whenever we have a conservative forces are acting on any system, we can apply conservation of mechanical energy, clear. So I can apply here conservation of mechanical energy between point A and B, clear. So now I am writing here initial kinetic energy plus initial potential energy, this should be equal to final kinetic energy plus final potential energy, clear. Now you can say here initial speed is given to you, I am assuming that is v, clear. So half of mv square plus, now if I talk about potential energy, clear. So let's suppose I am saying this is a center of this earth, clear, and radius we know, let's suppose I am saying that is re, clear, or you can say that is capital R, clear. So we can say, just a minute, yes, so we can actually we are taking here value of radius, that is capital R, clear. So from here you can write value of potential energy, clear. So what is expression of potential energy? Potential energy expression we have minus g me. Me is what? This is mass of earth, clear. Me, m divided by, I can say that is r, clear. R is the radius of this earth. Now if we are talking about point number B, at point number B we are having final velocity 0. It means I can say kinetic energy at that point is 0. And what about potential energy? Potential energy we can write like this, this is minus gmem divided by, I can say what is total distance from center of earth, that is r plus h. So we can write like this, this is r plus h, clear to everyone. So now from here we can write like this, half of m, or you can say m and m, this one is cancelled out, clear, this one is cancelled out. Now if you multiply with 2 both side, we can also write like this, v square minus twice g me divided by r, and this should be equal to minus 2g me divided by r plus h, clear. So from here we can write like this, this is 2g me divided by r plus h, this is equal to, clear, 2g me divided by r minus v square, clear. So if I take here LCM, I can also write like this, 2g me divided by r plus h, this should be equal to, clear. If we take here LCM, that is capital R, clear. So we can write like this, this is 2g me minus, I can say this is v square r divided by, we can say that is r, clear. So now if you multiply, if you cross multiply, you can write like this, r plus h, this should be equal to 2g me and multiplied with r divided by, clear, divided by, this is 2g me minus v square r, clear. Now what we can do, now we have to put all the values here, clear. So definitely there is some complex calculation is here. So now concentrate, we are actually going to solve this expression, clear. Concentrate on the screen. Yes. Now concentrate. Clear? From here we can write like this, R plus H, this is equal to 2G ME R divided by 2G ME minus V square R. Clear? Now we can put here all the values. So I am writing here R plus H, this should be equal to 2 multiply value of capital G. Value of capital G we have 6.67 into 10 to the power minus 11. So 6.67 into 10 to the power minus 11 multiply mass of earth. Mass of earth means we can say that is 6 into 10 to the power 24 kg. Clear? So 6 into 10 to the power 24 kg multiplied. Okay, what about radius? Radius of earth we have 6.4 into 10 to the power 6. Clear? It is divided by, we can say 2 multiply 6.67 into 10 to the power minus 11 multiply. What is mass of earth? Mass of earth is given 6 into 10 to the power 24 minus. What about velocity? Initial velocity of rocket, that is 5 km per second. So we can write like this. This is 5 into 10 to the power 3 whole square multiply radius of earth. Radius of earth we have 6.4 into 10 to the power 6. Clear? Yes. Now we have to solve this expression. Now you can say, sir, it's a lengthy calculation. Yes, we have, but if you solve it wisely, definitely you can actually decrease here number of terms. Clear? Now concentrate. First I am removing this expression. Clear? So that we get some space here. Yep. Now let us try to understand. First I am saying this is 2 multiply 6.67 multiply 6 into 10 to the power 24 and this is 10 to the power minus 11. So I can say this is 10 to the power 13 multiply 6.4. Clear? And we have here 10 to the power 6. So we can say 10 to the power 90. Clear? Again I am saying 10 to the power minus 11 24. That is 10 to the power 13 and 6 19. Clear? Now we can also write like this. This is what? 2 into 6.67 into 10 to the power we can say again 13 multiplied with I can say 6 minus this is what? 25 into 10 to the power 6 multiply 6.6 and I can say here we have 10 to the power 6 also. Clear? It means I can write like this. If I remove this 10 to the power 6 and I can say here we can write this is 10 to the power 12. Clear? So now what we can write here, we can say R plus H, this is given by, R plus H is given by, now this is 10 to the power 13, listen carefully, 10 to the power 13, if I remove this decimal I can say this is 100 and if I remove this decimal I can say this is 10. So now we can say this is 10 to the power 11 and this one is also 10 to the power 11. Clear? So from here we can say R plus H. R plus H is given by 2 into 6.67 into 6 into 6.4 into 10 to the power 19 divided by, now listen carefully, 2 into 667 into 6. You can take here one observation, 10 to the power 11 and 10 to the power 11. We can take common and we can cancel with 10 to the power 19. So directly you can say here we are having 10 to the power 8. Clear? So this value we are getting only 10 to the power 8. Clear? Now what we left here, this is 2 multiply 667 into I can say 6. Clear? Minus 25 into, now I can say this is 64. Clear to everyone? Now we have to solve it. So how can we say, we can actually write like this. Listen very carefully what I am saying to you. R plus H, this is equal to, here we have 6.67. Clear? Here we have 667. Clear? And here we have 64. Clear? So how can we write? We can first actually just we can write like this. This is 30, we can say 6.67 into 12 into 6.4 multiply 10 to the power 8. Clear to you? 6.67 multiply 12 multiply 6.4 into 10 to the power 8, and I can say this is 12 multiply 667 minus 25 into 64. Clear? So now if you observe here, you can see we can take here, let's suppose if I am dividing here with 10 and multiplying with 10. Listen carefully what I am saying to you. If I am multiplying with 10 here in this expression, multiplying with 10 and dividing with 10. So if I multiply, I am dividing, I can say this is 2.5, and if I am multiplying, I can say this is 640. Clear? So approximately I am saying this 667 and 640 approximately equal to same, because we have to simplify this expression. That's why I am taking. Actually I know this is not very near to each other, but let's suppose if we are saying this one and this one is approximately same. Clear? I can say here this is 100. So from here we can write here r plus h. This is given by this one and this one is cancelled out. Clear? So directly I can say that is 12 multiply 64 into, here we have 3 10 to the power 5 divided by 12 minus 2.5. Clear? Clear? Yes. Now we can say this is 12, this is 2.5, so we can say this is 9.5. Let's suppose I am taking 10. Clear? So if this is 10, I can say 12 into 64 into 10 to the power 4. Clear? From here if you multiply, you can say this is 8, we have 4, 12 6, that is 72. I can say this is 76 into 10 to the power 4. Clear? So approximately what I am saying to you, you will get here value r plus h. This is equal to 8 into 10 to the power this one 8 into 10 to the power 6 meter. Clear? You will get here approximate this value r plus h. Clear? But now what is my objective in this question? My objective is clear. We have to calculate here value of h. Clear? So how can I calculate value of h? Yes. Now we can say, we can write like this. This is 8 into 10 to the power 6 meter. Clear? So value of h, this is given by 8 into 10 to the power 6 minus r. Clear? So 8 into 10 to the power 6 minus value of r. Value of r we have, we can see that is 6.4 into 10 to the power 6. Clear? So from here I can write like this, 1.6 into 10 to the power 6 meter. Clear? 1.6 into 10 to the power 6 meter. Clear? And from here you can also say, we can write like this, this is 1600 kilometer. Clear? So this is a value of height, that is height that is gained by this rocket before, we can say before coming to rest. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.18, and in this question it is given to you, the escape speed of a projectile on the earth's surface is 11.2 km per second. Clear? A body is projected out with thrice this speed. What is speed of a body far away from earth? Clear? So let us try to understand this situation. In this question it is given, let's suppose I am drawing here, let's suppose this is earth. Clear? Let's suppose this is earth, and we are throwing any body from the surface of a earth with escape velocity. Clear? So escape velocity is what? Escape velocity is the minimum velocity that we can provide to any body so that it may leave the gravitational field, or it may go outside to the gravitational field of earth. Clear? So definitely we know, let's suppose escape speed, you know very well what is this value. This is equal to 11.2 km per second. Clear? So this is expression of escape speed. But now what I am saying to you, I am providing you, I am actually giving the velocity of this body, that is thrice of its initial velocity. I mean, I am providing here velocity of the velocity to that body that is thrice of its escape velocity. Now definitely when this body leaves, we can say that is gravitational field of an earth. Definitely here at this time it also having some more energy. Clear? Let's suppose this body is leaving this particular gravitational field with velocity v0. Clear? So now how can we calculate? Actually you know energy conservation, because this body or a rocket that is going with a under the influence of gravity. Now we know gravitational force is a conservative force. Conservative force means we can apply conservation of mechanical energy. So how can we write? Actually we can write like this. If I am talking about, let's suppose I can say kinetic energy initial condition, potential energy initial condition, this is equal to, I can say kinetic energy final plus potential energy final. Either you can write like this, or actually we have one more method by which we can solve this question. Clear? Okay. Now listen carefully. If I say here what is initial kinetic energy of this body, so I can say half of mve square. Clear? Clear? So now we can say this is a kinetic energy. Clear? But important part is here. Let's suppose I am providing initially escape velocity. Kinetic energy we have half of mv square. Clear? But let's suppose I increases this escape velocity 3 times. Then what will happen? So I can say, let's suppose that body is leaving gravitational field with velocity v0. So now we can say this is a change in energy, or we can say this is extra energy that this body have before leaving gravitational field. So this extra energy actually from where this body is getting? This body is getting from, because you are providing extra velocity. Clear? So we can write like this. This is 3 times of v square minus half of mve square. Clear? V is what? This is escape speed. So from here you can say m cancelled out. Clear? Half is also cancelled out. So from here we can write like this, v0 square, this is equal to 9 times of ve square minus ve square. Clear? So from here you can write like this, v0 square equal to 8 times of ve square. Clear? Or we can see v0, this is given by 2 under root 2 and this is ve. Clear? So now we can say this is a velocity. This is a velocity by which when this body is leaving this gravitational field, it is having that much of velocity. Clear? So we can write like this, 2 multiply I can say this is root 2 multiply 11.2. Clear? So we are getting our answer, that is 22.4 under root 2, I can say that is kilometer per second. Clear? So that much amount of velocity this body have before leaving this gravitational field. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.19, and in this question it is given to you, a satellite orbits the earth at a height of 400 km above the surface. Clear? So let's suppose we can see here. Yes, now it is given to you, a satellite orbits the earth at a height of 400 km, so above the earth surface. So let's suppose we are assuming, let's suppose this is earth. Clear? And let's suppose here we have a satellite, and this satellite is having height h equal to 400 km. Clear? This is given in a question. Clear to everyone? Yes. How much energy must be expended to rocket a satellite out of earth gravitational field? Clear? So first, can we find here total energy of this satellite? Yes or no? Can we find here total energy of satellite? Definitely. How can we find? We can write like this, total energy. Total energy equal to what? Kinetic energy plus potential energy. Clear? Kinetic energy. Kinetic energy is given by, let's suppose this satellite is having certain velocity. So I can say this is half of mv square minus gmem. Clear? Small m is the mass of satellite and me is the mass of earth, divided by, now what is total distance of this satellite from center of earth? So from center of earth you can say here we are having this radius, that is re, and re plus h. So I can write like this, this is re plus h. Now you know when this satellite is revolving around earth, at that time its orbital velocity is given by under root of gm upon r. Clear? So we can also write like this, this is half of m under root of gme divided by r whole square minus. Clear? I can say this is gmem divided by re plus h. Clear? So from here I can write like this, half of m g me upon r minus g me m upon Re plus H. Clear? So from here actually you will also write here that is R plus H, Re plus H. Clear? Why? Because this is orbital velocity, and orbital velocity is given by under root of gm upon r, and r is what? Distance from center of earth to the satellite position. Clear? So from here you can write like this: total energy expression of total energy, this is given by G small m capital Me divided by 2 times Re plus H. Clear? Re plus H minus G MEM divided by Re plus H. Clear? So from here I can write like this: total energy is given by minus G MEM divided by twice of Re plus H. Clear? So this is expression given for total energy. Clear to everyone? Yes. Clear? So now this is a total energy of this satellite, and let's suppose if I want to send this satellite out of gravitational field, it means I have to provide same amount of positive energy, so that the total energy of satellite becomes 0, and total energy of satellite becomes 0 only at infinity, or we can say when this satellite goes out of gravitational field. Clear? It means we have to provide total energy to this satellite, that is plus G MEM divided by twice Re plus H. Clear? Now our objective is to put here all the values and we will get our answer. Clear? So now concentrate. Yes, concentrate on a screen. Now we can write like this: total energy we have G MEM upon twice of Re plus H. So we can say, again I am writing G MEM divided by twice Re plus H. Now you can put all the values. What is value of capital G? Capital G value is given to you 6.67 into 10 to the power minus 11. So 6.67 into 10 to the power minus 11 multiply mass of earth. Mass of earth is given to you 6 into 10 to the power 24. Mass of satellite we have 200 kilogram. Clear? And it is divided by 2 Re plus H. Clear? Re is what? This is radius of earth. The radius of earth is given by 6.4 into 10 to the power 6 plus H. H value is given 400 kilometer. So I can say 400 into 10 to the power 3. Clear to you? So from here we can write like this: this is 6.67 multiply 6 into 2 multiply 100 and 10 to the power 24 26, and I can say this is 10 to the power 15. Clear? Divided by, now listen carefully, here we have value, that is you can say this is 4 into 10 to the power 5. Clear? And here we are having 64 into 10 to the power 6. Clear? Or we can say 64 into 10 to the power 5. So we can take here 2 into 10 to the power 5 common. Clear? Clear? So we can write like this: this is 64 plus I can say that is 4. Clear? So from here you can say this one we are getting 10 to the power 10. Clear? I am saying this 2 and 2 is also cancelled out. Clear? So now the rest calculation we are doing here. I think you are getting all my points. Definitely you can see here calculations are a little bit lengthy, and definitely because this is a gravitational chapter, so definitely you will find here calculation lengthy one. Clear? So now you can see here. Now we can say total energy. Total energy, this is given by 6.67 multiply 6 multiply 10 to the power 10 divided by, clear, I can say this is 68. Clear? Now listen carefully. If you remove this decimal, you can say that is 100. Clear? Or you can also write like this: this is 66.7 multiply 6 into 10 to the power 9 and divided by 68. Clear? Now 66.7, approximately I am taking 67, and I can say, let's suppose if we cancel out. Clear? Definitely this value will not come out to be perfectly 1, it will be something 0.9 something. Clear? So at that time we will find here total energy that is given, let's suppose 5.67, or that is 10 to the power 9 joule. Clear to everyone? It means if we provide this type, if we provide this much amount of energy to this satellite, at that time this satellite will leave the gravitational field of Earth. Clear? So this is all about this question. Now dear student, we are going to discuss question number 8.20, and in this question it is given to you, two stars each of one solar mass are approaching each other for a head-on collision. Clear? So let's suppose I am taking, this is a solar, let's suppose here we have a star, let's suppose this is S1, and let's suppose here we have another star, let's suppose S2. Clear? In this question it is given both are having mass equal to one solar mass, fine, approaching each other for head-on collision. When they are at a distance of 10 to the power 9 km, their speeds are negligible. So it is given here, distance between these two stars is 10 to the power 9 km, and their speeds are negligible. It means we can say initial. If I am taking this position as initial position, this system is having only potential energy. Clear? Because we are assuming both are at rest. It means initially both star is not having any kinetic energy. Clear? So I can write like this, if I am talking about total energy initially, total energy is actually here potential energy, and I can say this potential energy equal to minus G. Now both are having same mass, I am assuming that is capital M, and it is given here in this question solar mass. Clear? So Gm square divided by, I can say that is 10 to the power 12. Clear? Because we have to convert into meter. Clear? Now it is given here when they are at a distance, speed is negligible. Clear? What is the speed with which they collide? The radius of each star is 10 to the power 4 km. Clear? So let's suppose in second situation they are here at this position. Clear? And let's suppose I can say here this is S1 and S2. I am assuming here S1 is approaching in this direction with velocity v, and in this direction it is also approaching with velocity v. Clear? Now we can say here distance between these two center to center. Now for that one, you know, this is twice r, and radius of this each star is given 10 to the power 4 km. Clear? So now it means, now if I calculate here total energy at this position, we can say, we can write like this, here we are having kinetic energy plus potential energy. Clear? So I can write like this, total energy in this situation, kinetic energy half of mv square. This is kinetic energy of one, we can say one star. Clear? So what is total kinetic energy of two star? This is equal to half of mv square multiplied with 2. Clear? And what about potential energy? Potential energy is given by minus gm square divided by, here we are having distance, this is equal to twice r. Clear? So I can say that is 2 multiply r. R is given to you, this is 10 to the power 4 km. Clear? So we can convert into meter, so this is equal to 10 to the power 7 meter. Clear? So it means we can also write like this, this is equal to mv square minus gm square divided by 2 into 10 to the power 7. Clear? Now you know very well, actually they are moving towards each other due to gravitational force, and gravitational force are conservative force. It means conservative force is here, it means we can apply conservation of mechanical energy. It means directly you can write like this, if I write conservation of mechanical energy, mv square minus g m square divided by 2 into 10 to the power 7, this should be equal to, I can say minus gm square divided by 10 to the power 12. Clear? So from here you can say, we can write like this, mv square, this is equal to gm square divided by 2 into 10 to the power 7 minus gm square divided by 10 to the power 12. Clear? So we can say mv square equal to this one. Clear? Now you can observe here this we can say this factor, it is actually very less compared to this one, so we can neglect this quantity. Clear? So we can write like this, mv square, this should be equal to gm square divided by 2 into 10 to the power 7. Clear? From here we can write like this, m and m, this one is cancelled out. Clear? And we can say our objective here is to calculate speed. So directly we can say speed, we can write like this, v equal to under root of gm divided by 2 into 10 to the power 7. Just now we have to put all the values and we can get easily our value. Clear? So concentrate here. Now if I write here all the values, v, this is equal to under root of gm upon 2 into 10 to the power 7. Clear? So I can say this is given by g, 6.67 into 10 to the power minus 11 multiply. If I am talking about mass, we can say this is 2 into 10 to the power 30 and divided by 2 into 10 to the power 7. So from here you can write like this, 2 and 2, this one is cancelled out, and this is equal to under root of 6.67. Clear? 6.67 into 10 to the power 30 and minus 11 means 10 to the power 19, and we can say this is 10 to the power 12. Yes or no? This is 19 and we can say this is 10 to the power 12. So from here you can say actually we have 4, then we have square root 2, and if we have 9 we have square root 3. So here this is just between 2 and 3. So I am taking here, this is 2.6 into, this is 10 to the power 6, 10 to the power 6 meter per second. Clear? So when both stars are approaching to each other, at the time when there is a head-on collision between these two stars, speed of each star is given by 2.6 into 10 to the power 6 meter per second. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 8.21. Clear? In this question it is given to you two heavy sphere, each of mass 100 kg and radius 0.10 meter are placed 1 meter apart on a horizontal table. Clear? So let's suppose if I am drawing here, let's suppose this is a solid sphere. Let's suppose I am taking this S1. Clear? Let's suppose here we have another solid sphere, and let's suppose this is S2. Clear? It is also given here the mass or the radius of each sphere we know. Clear? Mass is given 100 kg and radius is given to you 0.10 meter. Okay, fine. It is placed 1 meter apart on a horizontal table. Clear? So I am taking this value r, this is equal to 1 meter. Clear? R is given to you, this is 1 meter. Fine. What is gravitational field? Actually here we have, this is gravitational field. Clear? So what is gravitational field and potential at midpoint of line joining the center of sphere? Clear? So let's suppose if I am talking about this point P. Clear? And let's suppose this point P is a midpoint. Clear? So I am telling to you this distance is what? This is 0.5 meter, and I can say this is what? 0.5 meter. Clear to you? Now our objective first here is to calculate value of gravitational field at point P. Clear? So now listen very carefully. Actually we know gravitational field, or we can say gravitational field intensity is a vector quantity. Clear? So first let us try to analyze the direction of electric field, we can say gravitational field, direction of gravitational field at point P. Clear? And after that we will decide that what is magnitude. Clear? So if I am talking about gravitational field acting at point P due to 1, I can say this is in this direction, this is E1. Clear? And here we can say this is direction of gravitational field due to this sphere S2 at point P. Clear? Now if I calculate value of E1 and E2, definitely you will find here magnitude of E1, this is equal to E2, and this is equal to Gm over R square. Yes or no? Clear? So now we can say actually what is value of R we will take here. Yes. So let's suppose I am writing here, let's suppose this is R dash square. Clear? So we can write like this, G capital M divide by what is value of R dash? R dash value we have 0.5, so 0.5 whole square. clear. Now you can say actually mass of each sphere is same, clear, and distance of this point from center of each sphere, that is also same. It means we can say we are getting same magnitude, clear. So whenever we have same magnitude, and we can say gravitational force is acting in an opposite direction, so same magnitude, opposite direction, it means we can say net gravitational field is 0, clear. So directly you can say here value of gravitational field intensity, net gravitational field intensity, this is given by 0 Newton per kilogram, clear to everyone. But if I talk about net gravitational field at point P, clear. So net gravitational field at point P, this is given by equal to V1 plus V2, clear. Actually what is value of V1? I can say V1 value we have, that is minus we can say minus Gm divided by distance, we can say that is r dash, clear. Now here we can say due to this sphere we have minus Gm upon r dash, clear. Always keep in mind gravitational potential is a scalar quantity. Here we do not take care about direction, because we can say in gravitational potential we will not find any direction, clear. So directly you can say here gravitational potential is given by minus 2 Gm divided by r dash, clear. Now we can put here value and we can got our answer. So minus 2 multiplied value of capital G 6.67 into 10 to the power minus 11 multiply what is value of mass. Mass is given to you 100 kilogram, this is 100 kilogram, divided by value of r dash. R dash is given 0.5 meter, so I can say this is 0.5, clear. So from here you can say we can write this is 1 by 2, this 2 goes to numerator, this become 4, and 4 multiply 6.67, clear. And I can say this is 10 to the power minus 9, clear. So now we can write like this, value of Vp, this is given by 4 multiply 6.67, so I can say we have 8, we have 2, we can say this is 6, we have 2, and we can say that is again 26. So 26.68 multiply 10 to the power minus 9, I can say this is volt. Yes or no? Yes or no? And here we will get this value in minus. So final answer we are getting minus 2.668 into 10 to the power minus 8 volt, clear. So this is value of gravitational potential at point P, clear. So I think this question is clear to you. Now student, we are going to discuss question number 8.22, and in this question it is given to you, we have a geostationary satellite orbits the earth at a height of nearly 3600 kilometer from the surface of earth, clear. So let us try to understand this question. Let's suppose we have this is earth, clear, and let's suppose here we have a geostationary satellite, and this geostationary satellite it at a height of 36000 kilometer from surface of earth. This is given in a question, clear. And let's suppose we are taking this is center and this is radius of earth, and we know this is equal to 6400 kilometer, clear to you. Now our objective in this question is to calculate what is potential due to earth gravity at this site of satellite, clear. So now you know very well gravitational potential, this is given by minus times of Gme divided by, we can say 6400 plus 3600, clear, or we can say minus Gm upon r. So this is in kilometer, we can convert into meter also, clear. So from here we can write like this, minus 6.67 into 10 to the power minus 11 multiply what is mass of earth. Mass of earth is given 6 into 10 to the power 24, clear, and it is divided by we can say here we have 4 to we can say this is what 4, clear, yeah, 4 to 4, and then we can say this is 00, yes or no, because let's suppose 36 or we can say 6, that is 4200 and 400 extra, clear. And now we can say it is multiplied with 10 to the power 3, clear. So from here you can calculate, easily calculate minus 6.67 into 6 into 10 to the power 13 and divided by, I can say 42400 multiply 10 to the power 3, From here you can say this is 10 to the power 10. Clear? Now if you multiply, you can write like this, because it is in kilometer. So we can also write like this, V, this is equal to, first multiply 6.67 with 6. Clear? So we can say this is, we have to, clear? Just a minute. Yes. Now from here you can see, we can take here this value, that is 2, we have here 4, so this one is 0. Yes, we have again 4, so again we can say that is 40. Clear? And we can put here this is dot, decimal, and multiplied with 10 to the power 10 divided by, now here we have 4200, we can also write like this, this is 42.4 into 10 to the power 3. Clear? From here you can say this is 10 to the power minus 7 in denominator. Clear? So we can write like this, this is V equal to minus 40.02 divided by 42.4 multiply 10 to the power 7, and this is joule per kilogram. Clear? Now we can say this is 40, this is 42.4. So definitely we will get here value like this, minus 0.943 into 10 to the power 7 joule per kilogram. Clear? So we can say this is value of gravitational potential. Clear? So at a geostationary satellite. Clear? So this is all about this question. Now student, we are going to discuss question number 8.23, and in this question it is given to you, a star 2.5 times the mass of sun and collapse to a size of 12 km rotate with the speed of 1.2 revolution per second. Clear? So in this question it is given to you, mass of this star, this is 2.5 times of mass of sun. Clear? Now mass of sun, that is given by 1 solar mass, and value of 1 solar mass we have, it is also given in a question, 2 into 10 to the power 30 kilogram. Clear? Always keep in mind, let's suppose if we need any numerical value, definitely that will be given to you in a question. Clear? So mass of sun is given 2 into 10 to the power 30, so we can write like this, this is 5 into 10 to the power 30 kilogram. Clear? Now listen carefully. One more thing is given to you, radius, or we can say distance. So I am taking this value r, that is equal to 12 kilometer, so we can write in meter also. Clear? Now it rotates with a speed of 1.2 revolution per second. It means I can say this is value given to you, frequency 1.2 revolution per second. So now can we convert it into radian per second? Yes, we can find here omega or angular speed, and we can say if we multiply like this. Clear? So definitely we can say here this is 2.4 pi. Clear? Radian. Clear to everyone? Yes or no? 1.2 revolution per second is given to you. We can write like this, 2 pi multiply f. So this is 2.4 radian, 2.4 pi radian. Clear? Now listen. Now first, can we find here acceleration due to gravity due to this star? Clear? Actually, what is concept behind it? First of all, here we will calculate acceleration due to gravity due to this star. Clear? After that we calculate what? We will calculate here centripetal acceleration, and then we compare. If acceleration due to gravity is more compared to centripetal acceleration, at that time we can say that object always remains stick to this surface of this star. Clear? So first we can calculate here acceleration due to gravity. I can say this is given by gm upon r square. Clear? Value of g we have 6.67 into 10 to the power minus 11. Clear? Multiplied with m. M is what? That is mass. Mass is given 5 into 10 to the power 30 divided by, I can say value of r. Value of r is given, that is 12 into 10 to the power 3. So we can say 12 into 10 to the power 3 whole square. Clear? Now you can simplify it. So we can also write like this, 6.67 multiply 5 into 10 to the power 19. Clear? And here we can write like this, 12 multiply 12 and multiply 10 to the power 6. So I can say this is 10 to the power 13. Clear? This is 10 to the power 13. Clear? So you can say here 6.67 into 5 and multiply 10 to the power 13 divided by 12 into 12. Clear? So if you multiply, you can say here we are getting, this is 5, we have 3, so this is 33, we have 3, this is 33.35. Clear? And it is divided by 144. clear, and multiplied with 10 to the power 13, and we can say this is meter per second square, clear. Definitely unit we will find this in meter per second square. Now you can say, let's suppose if I take here 14.4, listen carefully, 14.4, clear, it means I am just dividing with 10, it means I will multiply with 10 also, so I can say this is 10 to the power 12, clear. From here you can say approximately you are taking 2.2 into 10 to the power 12 meter per second square. So this is an approximate value of acceleration due to gravity, clear. Now we will calculate here what is centripetal acceleration here, clear. So centripetal acceleration that is given by, now centripetal acceleration that is given by yes, we can write like this, centripetal acceleration AC, this is equal to omega square r, clear. Now value of omega we have, yes, we can calculate, this is 1.2 revolution per second, so we write here this is 2 pi multiply 1.2 whole square and multiplied with r, clear. R is given to you, yes or no? Yes, that is 12 kilometer, clear. So we can say this is 12 multiplied 10 to the power 3, clear. So from here we can say, we can write this is 4 pi square multiply 1.44 multiply 12 into 10 to the power 3, clear. Now we know pi square approximately we are taking 10, so 4 multiply 1.44 multiply 12 into 10 to the power 4, clear. Now you can say if you multiply 12 with 4, that is 48 and 1.44, so approximately you are taking 1.5, so 48 multiply 1.5, it means you can write like this, that is 48 multiply 3 by 2 into 10 to the power 4, clear. So now we can say this is 24, so we can say that is 72 into 10 to the power 4 meter per second square, clear to you. So now from here you can see if you compare acceleration due to gravity and we can say centripetal acceleration, definitely you can say value of acceleration due to gravity is more compared to centripetal acceleration, clear. So definitely we can say when acceleration due to gravity is more, definitely that object always remain stick to that surface of that star, clear. So this is all about this question. So dear student, we are going to discuss question number 8.24, and in this question it is given to you a spaceship is stationed on Mars, clear. So let's suppose I am taking here, this is Mars, clear, Mars, clear. It is given here a spaceship is stationed on Mars, and spaceship means, let's suppose we are placing spaceship in any orbit of Mars, clear to you. Now it is given here how much energy must be expended on the spaceship to launch it out of solar system, clear. So let's suppose we place this spaceship at a height h from this surface Mars, clear. But important part in this question we have to launch it out of solar system, clear. So at the solar system we can say at the center we have sun, so definitely here we will take gravitational force into consideration due to sun, clear. So now we can say, can we write here total energy of this spaceship, yes or no? Yes. So total energy expression, this can be written like this, total energy, this is given by kinetic energy plus potential energy. Kinetic energy is given by, let's suppose this spaceship is going with velocity v in tangential direction, clear. So half of mv square minus gms m divided by, I can say, let's suppose this is r plus h, clear to you. And here r is what? We can say r is a radius of Mars, clear. Now we know here what is v. V we can say this is orbital velocity, so we can put here expression of orbital velocity, clear. So 1 by 2 m, this m is a mass of this spaceship, clear. And we can write like this, under root of g m, we can say under root of g ms, or we can say it is divided by r plus h, clear, and it is whole square, clear, minus g ms m divided by r plus h, clear to you. So from here we can write like this, 1 by 2 m Gms over R plus H minus Gms m upon R plus H. Clear? From here we can write like this. This is equal to minus 1 by 2 Gms m divided by R plus H. Clear to you? So from here we can see total energy expression, this is given by minus Gms m divided by twice of R plus H. Clear to you? So this is total energy that is contained by this spaceship. Clear? Now let's suppose if we want that this spaceship will go out of the solar system, it means we have to provide same positive energy to this spaceship. Clear? So we can see total energy given to spaceship to send it out of solar system, and it is given by plus Gms m divided by twice of R plus H. Clear to you? So now we can put here all the values. Clear? And we can say here what is total energy required. Clear? So now concentrate here. Yes. So now we can put here all the values. So I am writing here all the values. Total energy given by Gms m divided by twice of R plus H. Clear? Now what is value of capital G? Capital G value we have 6.67 into 10 to the power minus 11. So 6.67 into 10 to the power minus 11 multiply mass of we can say ms. So we can say mass of we can say solar, or we can say mass of sun. Mass of sun is given here, we can say that is 2 into 10 to the power 30 kilogram, and this is equal to 1 solar mass. So 2 into 10 to the power 30 divided by mass of spaceship. Mass of spaceship is given, that is 1000 divided by, I can say 2 times of capital R. Capital R is what? This is we can say radius of orbit of Mars. Clear? So we can say radius of orbit of Mars, and we also know here that is H. Clear? So H we can say it is given here. This is mass of a Mars is given to you, okay, but radius of orbit of Mars is also given. So we can say this radius directly we can say we have 2.28 into 10 to the power 8 multiply 10 to the power 3. Clear to you? Yes or no? Yes. One more thing is given, that is radius of Mars, that is 3395 kilometer. Clear? So actually what is the meaning of this one? This is a radius of orbit of a Mars, clear, plus radius of Mars. So we can say this is given by, or you can directly say here it is not required. Clear? Actually this distance is what? This distance is a distance of this spaceship from a center of Mars. Clear? So directly it is already given that radius of Mars is given 2.28 into 10 to the power 8 kilometer. Clear? So from here directly we can say this is equal to this one. Clear? If you write here H, actually we have already included R plus H. Clear? So from here we can solve it. So we can write like this, 6.67 into 2 into, now we can say this is 10 to the power 30, 10 to the power 33, and we can say this is 10 to the power 22. So 10 to the power 22. Clear? 6.67 into 2 into 10 to the power 22 divided by, I can say 2 multiply 2.28 into 10 to the power 11. Clear? So from here we can say this is given by 10 to the power 11. Clear? This one and this one cancelled out. Clear? So from here you can write like this, this is 6.67 into 2.28 into 10 to the power 11. Clear? So if you solve it approximately, we can say you will find here answer. We can say this is near about 2.5, clear, and this is near about 6.5 something. So directly we can say this is 2 point something you will get. Yes. So from here we are getting 2.9 into 10 to the power 11, and this value we have, that is joule. Clear? It means if we provide this much amount of energy to this spaceship, at that time that spaceship it will go out of gravitational field of a sun, or we can say it will go out from go outside to the solar system. Clear? So this is the solution of this question. Clear? So this is all about this question. Now student, we are going to discuss question number 8.25, and in this question it is given to you, a rocket is fired vertically from the surface of a Mars with a speed of 2 km per second. Fine. If 20% of its initial energy is lost due to meridian atmospheric resistance, then how far will the rocket go before the surface of a Mars before returning to it? Clear? So again, definitely you can see from this language of this question we can apply here total energy conservation. Clear? So first I am writing here total energy of a satellite. Clear? First of all, this is rocket. So in this question it is given, a rocket is fired vertically from surface of a Mars. Clear? With the speed of 2 km per second. So we can say from a surface of Earth, we can write like this total energy. Clear? Total energy is given by half of mv square, clear, minus we can say this is G capital M upon M, and we can say that is R. Clear? R is what? This is radius of Mars. Clear? So this is total energy at a surface. Clear? And it is also given initially rocket is having velocity 2 km per second. Clear? Now it is given 20% of its initial energy is lost. Clear? It means now remaining energy is what? 80%. So we can also write like this. Now 80% means we can say this is 4 by 5. Yes or no? Because this 80% means 80 by 100, and this is equal to 4 by 5. So 4 by 5, 1 by 2 mv square minus G capital M divided by R, and this should be equal to, clear, 4 by 5 multiply half of mv square minus G capital M upon R. This is equal to I can say minus G capital M small m, and we can say let's suppose this rocket goes to a certain height h before coming to a rest. Clear? So concept is very simple. First we are writing here total energy at a surface of Mars. Clear? After some time when rocket is going in an upward direction, definitely there is an acceleration due to Mars is acting, and at that time we can say after some time rocket is having velocity 0. Clear to everyone? So from here we can write like this. Now if you multiply it, we can say this is 2 by 5 mv square minus 4 by 5 G capital M small m divided by R, and this should be equal to minus capital M small m divided by R plus H. Clear? So from here we can write like this, small m and small m, this is cancelled out. Clear? So from here if you take 2 by 5 common, you can write like this, V square minus 2gm divided by R. Clear? And this should be equal to minus gm over R plus H. Clear? So from here we can write like this, if you take here LCM, finally you can say this is given by 2 by 5 V square R minus 2gm divided by, we can say capital R, this is equal to minus gm over R plus H. Clear? So can we find here value of R plus H? Yes. So R plus H, this is given by minus 5R gm divided by, I can say this is 2 V square R minus 2gm. Clear? Clear? Now we know here value of capital R is given to you in a question, and this is equal to 3395 km. Clear? But we will put it after some time. This time I am writing here R plus H, this is equal to minus 5 into r. Value of r is given 3395. 3395 kilometer we can convert into meter. Clear? Now value of capital G. Value of capital G we have 6.67 into 10 to the power minus 11. Clear? Multiply mass. So mass of a Mars is given 6.4 into 10 to the power 23. Clear? It is divided by 2. Now we can say V square R. So rocket is actually having velocity 2 km per second. So I can say this is 2000 multiply 2000 multiply. Now I can say value of capital R. Clear? So value of capital R, I am saying value of capital R, this is what? 3395 kilometer. 3395 kilometer. Clear? Minus this is equal to 2 into 6.67 into 10 to the power minus 11 multiply capital M. Clear? Capital M is given to you, that is 6.4 into 10 to the power 23. So I am writing here 6.4 into 10 to the power 23. Clear? So this is all about all these values. Now we have to calculate this calculations. Clear? So definitely it's looking like a tedious calculation, but let us try to simplify this calculation as much as possible. Clear? So now concentrate on a screen. Yes. Now concentrate. From here we can write like this, R plus H, this is equal to, first I am writing like this, this is minus 5 into 3395 multiply, I can say 6.67 and 6.4. So 6.67 into 6.4. Now we can say 10 to the power 3, 10 to the power 23, 10 to 26, and this is minus 11. So we can write like this, this is multiply 10 to the power 15. Clear to you? And it is divided by, now we can simplify it to multiply. Now we can say 2 multiply to 4. Clear? 4, and we can say this is 3 into 3395. Clear? Multiply. This is 10 to the power 3 and we have 10 to the power 6 here. So 10 to the power 9. Clear? Minus, I can say this is what? 10 to the power 23 minus 11 means we can say 10 to the power 12. Clear? And if we remove here these decimals, this becomes 10 to the power 9. So at the end I am writing this is 10 to the power 9. Clear? Now we can write here 2 multiply 667 multiply 64. Clear? 2 multiply 667 multiply 64. Clear? Clear to you? So from here we can write like this, R plus H, this is equal to minus 5 into, okay, we can say this one is what? 3.2. Clear? Minus 5 into 3395 into 6.67 into 6.67 into we can say 3.2. Listen carefully. Minus 5, 3395, 6.67, 3.2, and we can say from here if we take common 10 to the power 9, we can write like this, this is 10 to the power 6. Clear? Divided by. Clear? We can say here we have 4 into 3395 minus 2 into 667 into 64. Clear to you? So now we will try to simplify this calculation. So now listen carefully. From here we can say, we can write here, if we divide with 3395 in numerator and denominator as well. So we can say this is 5 multiply 6.67 into 3.2 into 10 to the power 6. It is divided by, I can say 4 minus. Now what is multiplication of 667 and 128? Clear? So we are just multiplying 667 and 128. Yes. Now concentrate here. We can say actually here I am writing like this, 667 multiply 128. Clear? So we can say here we have 6, we have 5, 48, I can say 53, we have 5, clear? 48 and we can say this is 53, clear? Now we can write like this is 14, we have 1, this is 13, we have 1, this is 13, clear? 7, 6, 6. So now if we add, we can write here this is 6, this one is 7, 3, 3, 6 and 7. We can say this is 13, we have 1, 6, 3, 9 and we can say 15, we have 1, so 2 and we can say this is 6. Clear? So from here we are getting 8, 5, 3, 7, 6. Yes or no? So we can write like this, this is 8, 5, 3, 7, 6 divided by, we can say this is 3395. Clear? Because we divided here 3395 in numerator as well as denominator. Clear? So approximately we can take this is 34. Yes or no? This is approximately 34 and we can say this is approximately 86,000. Clear? So 34 means this is we can say 22 point something. Clear? So directly we can say, I am just saying this is approximately 2.8. Clear? So we can write like this, R plus H, this is given by 5 minus 5 into 6.67 into 3.2. Clear? 3.2 multiply, I can say that is 10 to the power 6 divided by, I am taking it approximately we can say 2 point something. Clear? So this one is 2 point something and here we can say this is 20 point something. Yes or no? Because if you multiply it with 34 into 2, so 68, and if you multiply 3, that is 99. So approximately we can say 28 point something. So directly you can say this is 4 minus 28, let's suppose. Clear? So from here we can say this is 24. So R plus 6, this is equal to minus 5 into, let's suppose I am taking this is 6, this is 33.2 and this is 10 to the power 6 divided by, I can say this is 24. Clear? Minus minus cancel, this one is 4, I can say this is 10, this one is 8. Clear? So from here you can write like this, R plus H, this is equal to 40 into 10 to the power 6 divided by 10. Clear? So approximately we are getting here value R plus H, this is equal to 4,000 kilometer. Yes or no? 4,000 kilometer. But actually if you calculate it, you will find here correct answer, that is 5040 kilometer. Clear? Definitely, because calculations are lengthy, so we are taking here approximation, but actually if you calculate you will find this result 5040 kilometer. Clear? So from here you can calculate, yes, from here you can calculate value of we can say small h. Clear? So how can we calculate value of small h? Very simple. We know value of capital R. Capital R value is given to you 3395 kilometer. Clear? So directly we can calculate here value of capital H. Clear? Value of capital H. So from here we can see, from here we can write like this, R plus capital H, this one is equal to 5040 kilometer. Clear? So we can see H is given by 5040 minus value of capital R. Value of capital R we have 3395. Clear? So from here you can see this is 5, we have 3, we can say that is 4, we have 9, we can say this is 6 and 1. So we are getting here answer, this is 1645 kilometer. Clear? So definitely we can say this rocket will move from surface of a Mars at a height of 1645 kilometer. When that rocket reaches to a certain height, at that time it comes to rest and again it returns to the surface of Mars. Clear? So this is all about this question. Clear? So dear student, this is all about all NCERT and exercise solutions of chapter number 8, Gravitation. Clear? And now definitely you will benefit from all these questions, and definitely you will learn here some theory concept with the help of these questions also. Clear? Although you will find here the calculations are tedious, but if you solve it by taking some approximation, definitely you can find the solution as soon as possible. Clear? So this is all about this chapter. So thank you so much.